I'm going to come back to example 1 in a second, but let's go to example 3. This is where it gets weird. Imagine your age is 30. By the way, the proper abbreviation for years is actually a lowercase a for annually. So I use a Y, which I really shouldn't, because Y is yards in the US system. But whatever. Anyways, so if you see a little a by itself next to a number, just think years. So imagine you're 30 years old, you're an astronaut, and you have a daughter who is 5 years old. You're going to go on a space trip. In the year 2000, you're going to travel at 0.99 c, which is 99% of the speed of light, for a time of 6 years as measured by you on the spaceship. Jared, you're going to go out for 3 years and come back for 3 years. In other words, T0 is 6. How much time will have elapsed on Earth when you return? Use the time-dilation equation. So this question is asking us to find T. Time on the spaceship is 6. V on the spaceship is 0.99 c, 99% the speed of light. And this is where I said you want your big calculators out, but let's write the equation first. By the way, I'm going to give you enough practice. You might, Matteo, find your own shortcuts along the way, and if you do, that's great. I'm just not going to walk you. I'm going to have you find them on your own. So the time dilation equation says this: time on Earth is equal to time on the spaceship divided by the square root of 1 minus, and I'm going to write it the new way I showed you, V over C all squared. Why did I write it that way? You'll see in just a second. Adrian, what's T0? How much time elapsed on the spaceship? 6 years. Divided by the square root of 1 minus. Adrian, what's V? 99% the speed of light divided by C, and it's that, whoop, it's that whole bracket all squared. Adrian, the reason I wrote it this way is there a C right there? Yeah. Is there a C right there? Yeah. Is there a C on the top of the fraction? Say yes. Yeah. Is there a C on the bottom of the fraction? Yeah. You know what happens to those C's, folks? That's why I wrote it that. That's why typically instead of writing V squared over C squared, Jared will put V over C in brackets all squared, because if you're lucky, if you do the speed as a percentage of light, the C's will cancel. In fact, what I really get is this: 6 all over the square root of 1 minus 0.99 squared. Now, you may find shortcuts to type this into your calculator, especially if you get good with brackets. Of course, Nick has his calculator out in front of him. I've advised you do the bottom first. So the way I do this, I go 1 minus 0.99 squared. I hit equals. Then I go the square root of that. I hit equals. And then I go, what's on the top of this fraction? 6 divided by that answer. Hopefully I've done a rant about the importance of getting a good calculator with an answer button in particular. And it turns out, back on Earth, how many years will have elapsed? 6 years on the ship, 42.5 years back home. And here's where it gets weird, because here's the obvious conclusion. What this means is this: if you left the Earth in the year 2000, you're going to come back in the year, sorry, not 2042, 2042.5. You're right, I did change it. So, how old was your daughter when you left?
5.
How many years have passed on the Earth? How old will your daughter be?
47.
How old were you when you left? How many years passed for you? How old will you be? You will be younger than your daughter, and there's absolutely nothing wrong with that. Totally doable under the laws of our universe. This is what Interstellar was getting at, by the way, if you saw that movie, at the very end where Matthew McConaughey ends up being younger than his daughter. Totally doable. Yeah? It gets cooler and weirder. Next lesson. But totally doable. What was that? Well, there was some wishy-washy stuff there too. By the way, the science consultant for Interstellar was Kip Thorne, and I think I sent you guys an email. He's coming as a speaker to Science World, I think in April. I don't know anything more than that yet, but I might go catch him because he is one of the biggie nerds in the whole, one of the top 3 guys in terms of black holes. Him, Stephen Hawking, and a couple other scientists. What this also means, though, in real life, Michael, is that if we do ever build ships that can go close to the speed of light, every trip will be a one-way trip, because if you're going on it, when you get back home, everyone you knew will be dead. Right? Specifically because there's no stars that are this close. If you want to go to a star that has a planet and it's like 50 light years away, it'll take you, well, if you're traveling at the speed of light, 50 years, we can't get to the speed of light, so it'll take you more than 50 years of your time. When you come back to the Earth, it'll be 100, 200, 500 years later. And that also makes it a risk because, wait a minute, if I leave on a ship that's traveling at 98% of the speed of light, and I'm planning on traveling for 10 years and then coming back for 10 years, so I'm willing to give up 20 years of my life. Well, if that ends up being several hundred years on Earth, how do you know that maybe while you were gone, they didn't find a way to get there instantaneously? How do you know that when you don't get to your planet, they might not be waiting for you there already? You thought you were going to colonize the planet, but somehow they invented warp drive in the 150 years while you were traveling for 5 years. On the Earth, 150 years went by. There's serious, the whole Star Trek future, you really got to think it through. There's weird stuff going on there. Example 4. Suppose a spaceship is traveling away from the Earth at 99.9%. Oh yeah, turn the page. I haven't forgotten it. Yep. Suppose a spaceship is traveling away from the Earth at 99.9% of the speed of light. Back on Earth, 1,000 years pass. How many years elapse for those on the spaceship? Hey, what's this question asking me to find? I'll give you a hint. Time. Which one? T0. So let's do our DFIC approach again, Julie. T0 equals question mark. So what's that 1,000? The regular T, time back on Earth. V is, well, it's 99.9%, but I can't use that. I need to change that to a decimal. What's 99.9% as a decimal? 0.999 of c, because it's of the speed of light. All right, let's write down our time dilation equation. T equals T0 all over the square root of 1 minus bracket V over C all squared. Pause. What's this question asking me to find? How would I get the T0 by itself? Well, there's that big square root thing. What's that square root thing doing to the T0? Adding, subtracting, multiplying, or dividing? Adding, subtracting, multiplying, or dividing? So how would I move that big square root thing over? Okay, so another version of this equation, T0 equals time back on Earth times the 1 minus V over C all squared. By the way, this square root expression has a fancy name. It's called the Lorentz Factor, and it's often called a gamma function, and I'll be talking about that later, because you're going to see whenever we look at Einstein's equations, this thing tends to show up in different locations. Okay, so 1,000 years have gone by on Earth. How much time elapsed on the spaceship? 1,000 times the square root of 1 minus 0.999c all over c all squared. Jilun, what happens to the c's? Cancel? So, I'm going to go like this. 1 minus 0.999 squared. Square root of that times 1,000. 1,000 years on the Earth? 44.7 years on the ship. That's a big difference. After 1,000 years, would anybody that you knew be alive back on Earth? No, but you're still alive. 44, especially if you were a child on a spaceship, if you went like a colony ship and families went, so you're like 10 years old, you would come back at age 54.7 years old to find, and again, think about 1,000 years in the future. Think about 2016 and compare that with the year 1016, how much technology change there was in that 1,000 years. Would you even really want to come back, or would it be so overwhelming that you would feel like somebody from the Middle Ages trying to figure out what was going on here? There's some really deep philosophical implications here. It gets even weirder, but cooler. So let's actually do a star journey, okay? Proxima Centauri is the closest star to the Earth. Proximate in your proximity means close. Okay, so it's the closest star to the Earth. I need to look up if there is a planet orbiting it or not, but let's suppose we want to just go visit it for research. It's 4.24 light years away. Now, a light year is how long it would take light to get there. Light would take 4.24 years to get there. Suppose I can build a spaceship that can travel at 80% of the speed of light. How long would the spaceship take to get there as measured by stationary observers here on the Earth? Well, okay. What's this question asking me to find? Time, and this is not a relativity question yet. I'm going to go back to basic physics 11. I'm going to say time equals distance over velocity, because we're talking about the people here on Earth, they're not moving. How far away is Proxima Centauri in light years? At what velocity? Can you all look up for a second? Because I need to do some little cheating here. The velocity is 0.8, technically times c, but actually light years contains a c in it, so please trust me, the c's would just cancel. If you want to know if you're going at 80% of the speed of light and you know how far away it is in light years, it's 4.24 divided by 0.8, which is what? So, for those of us staying home on Earth, we will expect that that ship gets there relative to us in 5.3 years. How long will it take to get there as measured by the observers on the spaceship? Well, now this wants me to find T0, time on the ship. And now we need to, because the spaceship is moving at relativistic speeds, now we better bring in Einstein's equation. I didn't bring it in here because Earth is standing still relative to us. You know what? We got the T0 by itself right up here. So can I go straight to this one? Yeah. T0 is going to be T square root of 1 minus V over C all squared. It's going to be 5.3 square root of 1 minus 0.8c over c all squared. Jilun, what happens to the c's? Yeah, there we go. So I pull up my trusty calculator. 1 minus 0.8 squared. Square root. Times 5.3 So even though on Earth they think it takes 5.3 years to get there, which it does relative to Earth, how long will we measure on the spaceship it taking us to get there? Now understand, that's kind of weird because Mr. Dewick, you're saying that's like we're getting there faster than the speed of light. No, time is slowing down for us relative to the Earth. Oh, it gets even weirder. So from the Earth, Proxima Centauri is 5.4 light years away. But it turns out that's not how far the spaceship will travel. For the spaceship, they're going to find that not only does time change, distance changes, because Einstein called this whole thing space-time. So as far as the spaceship is concerned, what distance did they travel? They traveled d equals vt. Which v? 0.8 times the speed of light. I'm going to ignore the c. Can you trust me? The c's are going to cancel because we're going to get, we want an answer in light years. Which time? 3.18. That's how long they traveled for. So even though when we measure the distance to Proxima Centauri from Earth and we get 5.3 light years, if they measured the distance while they were traveling, they would swear to you that Proxima Centauri was only 2.5 light years from Earth. And there would be no way to prove that they were wrong. I'm telling you, the universe, when you start traveling fast, bizarre stuff happens. Light, you know what? I'll just write it out. Here's what this means, and we're going to look at this in the next lesson. If you're traveling really, really fast, time slows down, but it also turns out length contracts. Distances get shorter. A ship that's traveling really fast, if you observe it while standing still, you will measure it physically shorter. And this actually has been proven. So right now at UBC, they have the Triumph, which is a particle accelerator. And one of the things that they do there is they make radioactive isotopes for Vancouver General Hospital. There's a little pipeline tunnel where they can send the radioactive isotopes. But those particles are traveling so fast that actually the distance that we've measured on the pipe is not what the particles experience. For them to do the numbers, they had to recalculate the perceived distance of the particles, and that's the distance they have to use for their calculations to make sure they end up at VGH. This has been demonstrated and proved experimentally all over the place. We just don't notice it because, sorry, we're all pretty slow. Some of you a little slower than others. Who was my late one? Okay. It gets even weirder. Hey, how much time elapses if you are traveling at the speed of light? Okay, so that's going to be our t0 because we're the moving object, which was t square root of 1 minus v over c all squared. What if you were traveling at the speed of light? What would you experience? I'm just going to leave the t there because I don't know quite what to put in. But certainly in here, I can go 1 minus c over c all squared. You okay with that, Adrian? Adrian, what's 5 divided by 5? What's 10 divided by 10? What's anything divided by itself? What's c divided by c? So if I hear you correctly, you're telling me this would be t times the square root of 1 minus 1. Adrian, in your head, what is 1 take away 1?
0.
What's the square root of 0, folks? Try it. 0. Oh. you get t times 0. What's anything times 0?
0.
Do you know how much time elapses if you're traveling at the speed of light? Photons don't experience time at all. So we like to say that when we're looking at the stars, oh, it took the photons 4.6 billion years to reach us from that star. Not according to the photon. As far as the photon is concerned, it was instant. It was instant. Photons don't experience time at all. Oh, it gets weirder. Because photons don't experience time at all, and because distance is velocity times time, as far as a photon is concerned, there's no such thing as distance. Every photon exists, as far as it's concerned, everywhere in the universe for all time, all at once. If they could think, that's what they would experience. It's a logical consequence of Einstein. Come on, that's pretty cool. Okay. So, even though for our stationary frame of reference here on Earth, we like to say that it takes light from stars thousands or millions or billions of years to reach us, in actual fact, relative to that beam of light, if it could think, how much time would have passed for it? Nothing. Everything is instant. Sorry?
Since, like,
okay, by the way, this is where now you start to look at this and say, okay, what other conclusions can we get to? And yeah, they get weird. I haven't told you this yet, but when you go faster, length gets smaller, time gets slower, mass gets bigger. But that's a whole other issue. Yes?
So, like, there's an instance like velocity times time.
Mm-hmm.
Since time is 0.
What that means is, for a photon, every distance is 0, which means to get anywhere in the universe is no distance, which means, if you want to think about it this way, they're everywhere in the universe all at once, as far as they're concerned.
So velocity is distance times time, though. But if time is 0.
Okay, but velocity, that one we have to say, we turns out that's what's special. The speed of light is the thing that's causing all this. The fact that the speed of light in a vacuum is constant no matter how you try and measure it, that's what's dominoing everything else into this. So if you try and then apply it back to velocity, that I'm going to say we can't do that one because the speed of light, the velocity, the fact that it's always the same, that's what's causing the rest of this stuff. Okay? Good thought. But that's what's causing the rest of this stuff. This is our universe. You know what? The whole Star Trek thing, they got around this by inventing, the reason if you watch Star Trek, they talk about warp drive. They got around this by inventing warp drive, which is sort of like a wormhole. They recognized, because there was techie guys behind the creation of Star Trek, if you tried doing things by actually just moving close to the speed of light, it's not a very explorable universe. It's doable, but understand, if you're going to go to a star that's like 20 light years away, and you're traveling at, let's say, 90% of the speed of light, or a relativistic speed, it's a one-way trip. Everyone you know is going to be dead by the time you're gone. There's a book that I just read about a month ago. It's a sci-fi book. It's called The Forever War. And the premise is Earth in the future is at war with an alien race, and so you sign up for the Marine Corps. And you serve for 5 years of space-time. But because you're traveling from planet to planet at relativistic speeds, your 5 years could be, depending on how fast and where you travel, 30 years back on Earth, 100 years back on Earth, 500 years back on Earth. And that's actually how they entice the Marines in. They say, here's what we're going to do. You're going to serve for 5 years. We're going to pay you your whole salary all up front right now. We're going to put it into a bank back on Earth. So even though it's going to be 5 years for you, it might earn 80 years of interest, depending on where we send you. It might earn 500 years of interest, depending on where we send you. You could come back and you could find out that you're a millionaire for 5 years of Marine service, if you survive. The book takes a twist because it follows two Marines that are the oldest living human beings, even though they've only served for 5 years. By a fluke, most of the missions that they've gone on have been traveling really, really fast, and so lots of Earth time has passed. And on their final mission, they come back to find something like 1,200 years have passed, and the war is long over, and nobody knows what the heck they're talking about because, oh, we've evolved enough that we can make peace with aliens, and we all get along now. And what, who, huh? So it's called the Forever War. There's some weird stuff can happen. Hey, let's do another one. This time, I'm not going to give you the speed of light as a percentage, or the speed as a percentage. This time, I'm giving you the speed as a speed in meters per second. So a spaceship is traveling that fast. It leaves the Earth and returns to Earth 100 years later relative to the Earth. How much time has passed for those living on the spaceship? What's this question asking me to find? Which time? Because there's always two of them. Okay, on the spaceship. So how much time passed back on Earth? Okay. Now, this time, I didn't give you the speed as a percentage, so V is 2.85 times 10 to the 8th. And this time, I'm actually going to have to type in C, the speed of light. And the speed of light is 3 times 10 to the 8th. We're going close to the speed of light, but not quite. Did we already get the T0 by itself on the previous page? I think we did. I think if I want T0 by itself, it was T times the square root of 1 minus V over C all squared. Right? By the way, the next thing we're going to start to look at is what if I want to find V? What if I want to know how fast I need to travel if I want weird stuff to happen? So that's going to be the toughest part. Anyways, let's keep going. 100 years of Earth time. Square root 1 minus, and I guess it's going to be 2.85 times 10 to the 8th. Yes, you're going to need to know where your scientific notation button is. Over 3 times 10 to the 8th. That number squared.
How would you type that in, Mr. Do It?
Okay. I think I would do what's inside the little bracket first. I would go 2.85 scientific notation button 8 divided by 3 scientific notation button 8. If I do that, I get 0.95. Then I would say, hey, what's outside the little bracket right there? I would go that number squared. You okay with that so far, Ty? Then it's really 1 minus that number. 1 minus answer button. Hopefully you're starting to clue in why I said the answer button is one of your most helpful, useful things. That whole thing is inside a square root. And then what's in front of the square root? Times 100. 31.2 years would have elapsed on the spaceship. I know what Karn's wondering. He's wondering, okay, if I want to pull some of this off, just how fast do I need to go? Example 8. Is this the last? Yep, last one. And I got some cool videos and stuff to show you too. Suppose the spaceship leaves the Earth traveling very fast. How fast? Really fast. It returns 20 years of Earth time later, but only 10 years have elapsed on the spaceship. In other words, let's suppose you wanted to have a 2-to-1 time dilation ratio. You wanted Earth time to go twice as fast as your time. How fast would you need to travel? So what's this question asking me to find?
T0. Velocity.
V. I think. By the way, this is as tough as we're going to get this because this is going to be fairly tough. I mean, don't kid yourself. Did they tell me t?
Yes.
What? Did they tell me t0? What's t0? 10? Well, let's write out our original equation. T equals t0 all over that. Ugh. What are we trying to find? V. Where is the V right now? Two things. Inside a square root. I'll deal with that later. But it's also on the bottom of a fraction. I don't like that. You know what? Let's rewrite it this way. We did that already. We said, oh, dividing by the square root is the same as timesing by the square root on the other side. Yes? Mateo, what am I trying to get by itself? Which is inside that there square root thing there? What's in front of the square root? What's the t doing to that square root? Adding, subtracting, multiplying, or dividing? Let's move that over. How could I move that over? Because that's not a v. Okay. So if I hear you correct, this is probably as intense a formula manipulation as we're going to do all year long. But I love the fact that most of you are following this. And actually what we're going to do is we're going to derive the equation, and then we're going to add it to our formula sheet one time. Okay. You said divide, yes? So I'm going to get this. The square root of 1 minus v over c squared equals t0 over t. Hey, in Math 11 this year, haven't you guys looked at square root equations? I think you might have, or you will be. So, well, see the v? That v is sitting inside the square root. I need to get rid of the square root. So you ready? Listen closely. How do I get rid of a square root? What's the opposite of square rooting?
Squaring.
So I'm going to go like this. Squared, squared. I got to do it to both sides, because remember your equation solving, you always had to do the same thing to both sides? Boy, going to run out of room here, Mr. Duke. I should have written smaller. Okay. I'm going to get this. So the square root on the left will vanish. I'll have 1 minus v over c all squared. And on the right-hand side, I'll have t0 squared over t squared. Because when I square the bracket, that's like squaring everything inside the bracket. Still ugly, but it's better. What am I trying to get by itself? Okay. What's sitting right, you're right, the v. What's sitting right there in front of the v? I know there's other stuff, but what's sitting right there? By the way, we're doing reverse bedmass. I'm doing my adding and subtracting before I deal with my squareds and square, because it's reverse bedmass. What's sitting right there? A minus. Here's what I'm going to do, Matt, because I hate having a negative in front of the thing that I'm trying to find. I'm going to do 2 steps at once. Look up, look up, look up, look up. I'm going to plus this to this side. At the same time, I'm going to minus this to that side. It's going to look like this. The 1 is going to drop down like a domino. I'm going to minus the t0 squared over t squared. And that's going to give me v squared over c squared. And that was because I don't want to have v with a negative in front of it. Oh, I can make anything positive by plussing it or minusing it to the other side. We're nearly done. We're almost there. Whew. See the v? What else is on the same side as the v? A c squared? What's that c squared doing to the v squared? Adding, subtracting, multiplying, or dividing? So how could I move that c squared over?
Multiplying.
C squared bracket 1 minus t0 squared over t squared. Now that equals v squared. What's my last step going to be? No, how do I get rid of a square root? This is about, in fact, I'm pretty sure this will be the most complicated formula manipulation that we do all year. I wouldn't expect you to be able to get this necessarily on your own, but I hope all of you followed our steps and, oh yeah, I see why you did that after you saw where we're going. Because now I can go, whoo! Time to plug in numbers. Well, this is complicated plug and chug. This is plug and chug with a vengeance. But, Karn, it's an interesting question. If you wanted time to go half as fast for you as the people back home, how fast would you need to travel? I kind of want to know. So it's going to be 3 times 10 to the 8th squared. That's C. 1 minus, what was T0? 10 squared over 20 squared. I'm going to do what's inside the brackets first, Adrian. I'm going to go 10 squared divided by 20 squared. I'm going to go 1 minus that. Now what am I going to do? I've taken care of this thing. What's happening between the two brackets right there? What's happening between the two brackets right there? Times. Times 3 times 10 to the 8th squared. Square root of that. (2.6) times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Or if you want to change that into a percentage of the speed of light, if you divide this by the speed of light, just like if you divide your test score by what the test is out of, and then times by 100, 86.6% of the speed of light. That'll give you a lovely 2-to-1 ratio of time dilation. Let's go all the way back to example 1. Last one. By the way, I'm hoping to give you a full half an hour to work on the homework because this is going to take some practice. Okay. It turns out this thing here has a fancy name. It's called the Lorentz Factor. But 1 over this thing here, this is your time dilation factor. This tells you how much, by what percentage, time will speed up or slow down or whatever. Say what? What speed is this ship traveling at? And this question isn't asking how much time has passed. It's asking by what factor is the time expanded or slowed down. So if I put a 0.5 c over c all squared, Jilun, what happens to the c's? They cancel. the bottom, I get this. 1 minus 0.5 squared. Square root of that. And the time dilation factor, because this is on the bottom, I'm going to go 1 divided by that. This is on the bottom of a fraction. Here's what we're saying. If you're traveling at half of the speed of light, the time on Earth is going to be 1.15 times the time on the space. Was it 1.15? 1.1547 times. This is what we call the time dilation factor. Time is moving 15% slower. 1.15 is 115%. Everybody experiences 100% of the time. They're getting a 15% slower amount of time. Or on the Earth, they're experiencing 15% more time. So there's what's called the time dilation factor. Okay? Hey, let's look at the homework. We need to practice this because it's heavy-duty calculator work. Now, on your formula sheet, I gave you this equation. If you want to, you can add the getting the T0 by itself equation. You can hand write it on your formula sheet. And if you want to, you can add the holy smokes. Here is the getting the v by it. V equals the square root of c squared bracket 1 minus t0 squared over t squared. You can add that one too. Okay? This is complicated enough, Matt, that I'm not going to force you into formula. It's Einstein. I'm not going to force you into formula manipulation for Einstein. But it's cool. What's your homework? I attach the answers at the very, very end, and I'm going to put a full answer key showing all my steps on pitmath.com. I'm also going to have a couple printed up here because for most of you, the error is going to be calculator work, I think. You got the rest of class. I said I was going to show you cool videos. I'll bring those out next class.